AC power, our topic for today and for this week, actually. It's not very long, just a few slides, a little bit of theory, some equations, and then we'll look at a couple of examples on Wednesday. All right, so power in AC circuits. Why is it important? And what are we going to do about it? Okay, now electrical power is transmitted over long distances, right? You may have seen overhead electric lines or overhead electric wires running from one end of, well, not one end, but all across the city. Doesn't matter where you live, but you may have come across these overhead electric lines, right? Especially if you go north over the mountains, you can see the electrical lines going across the mountains. There are some places inside the city itself where you can actually see these running through the parking lots. So every time electrical power is transmitted over long distances, a lot of that power is lost as heat. If you think back to chapter 1 on the first day of class, I mentioned that resistance of a piece of conductor or a piece of wire is negligible. When you perform theoretical analysis, all electrical wire has 0 ohms resistance, right? But in real life, a wire has resistance, it has inductance, and it also has capacitance. Resistance mathematically is given by the equation rho L over A. L is the length of that piece of wire. So if you take a 100-foot length of extension cable or extension cord, 100 foot is the length of that extension cord. It has some resistance, but that resistance value does not rise to the level of interference. You can plug a 100-foot long cable into an electrical power outlet, and at the end of that 100 feet, you would still expect 120 volts. It might have dropped to like 119 volts, perhaps, if it's not, very well made. But that does not rise to the level of interference. That 120 volts is not going to drop to less than 100. Does that make sense? Right? But when the length L runs into hundreds of miles, now that resistance and now that overhead cable does have some resistance. And every time electrons pass through an electrical conductor, it encounters that resistance, and a lot of that electrical power is lost as heat. So in a small wire or a small cable that runs like 6 feet or 10 feet or even 100 feet, it is not a big deal. But when it runs for hundreds of miles, it all adds up, and it is a big deal. On a side note, that is also the reason why appliances, especially like electrical heaters, have warnings on them that do not use an extension cord or an extension power strip with that heater. Is because the electrical heater draws a lot of current through the electrical outlet. If it draws a lot of electrical current, the wires tend to heat up. Most consumers will not look at the power rating of an electrical extension cord or an electrical power strip. Right? You would simply plug it into the wall and say, hey, it works. Let's just use it. Well, the electrical heater would end up drawing too much current from the power outlet. The power strip or the extension cord may not be able to handle all that power. It'll get heated up, and at some point, the wires will just explode, which is an electrical hazard, right? That is the reason why appliance manufacturers stick a warning on there. That is the absolute reason why. Anyway, coming back to our topic. So electrical power is transmitted over long distances. If power flows from the electrical utility company to the consumer. Consumers are of two kinds, residential and industrial. Okay. For residential customers, most of the loads would be resistive in nature. Okay, resistive in nature. There are some loads that would be considered inductive. Basically, your washers, your dryers, your electric heating coils in a cooking range, your HVAC unit, and the small compressor inside your refrigerator. They all have spinning mechanical motors, spinning mechanical machines, right? But they have electric coils in those mechanical motors. Those electric coils are coiled wires of electrical conductors. Electrically, they are represented as inductors. So any piece of wire, current carrying coil wound in a coil is an inductor. In residential environments, these loads would run maybe once or twice a week and for a few hours at that. Versus an industrial customer that have hundreds of these machines, some of them running 24/7. Okay, if you have a big factory or a workshop, even if it's not running 24/7, it's at least running 8 to 5 or 8 to 6, 5 days a week. That's a huge inductive load for the utility company. For a residential environment, it's negligible. Okay, so why is this important? Well, it's important because inductors are energy storage devices. Energy flows into an inductor. If you apply an AC voltage, the energy flows into the inductor in one half cycle. In the other half cycle, it flows back out, right? If it's a resistor, energy just flows one way and that's it. It might flow in and out, but it does not store any energy. For a capacitor and an inductor, it's different because they're energy storage devices. When you apply a AC voltage or current to an inductor or capacitor, the energy flows into the device and then it flows back out into the circuit. For an inductor, the energy flows into the inductor in the positive half cycle. In the next negative half cycle, the energy flows out. For a capacitor, it's the exact opposite. Capacitor and inductors are 180 degrees out of phase. So in a capacitor, the energy flows into the capacitor in the negative half cycle, and the positive half cycle, it flows out. Okay. The reason it's important is because this energy is associated with the reactance of the inductor and the capacitor. Okay. And hence this power is known as reactive power. It is different from the real power. This reactive power is real. It has a physical basis in real life. But similar to reactance, we use imaginary numbers or complex math to perform our mathematical analysis. Okay. If you ever read or hear the words imaginary reactance or imaginary reactive power, it is referring to the mathematical representation and not the actual physical basis. It has a physical basis in real life. It is real, but that term imaginary is associated with the mathematical representation. It is a mathematical reference. So again, similar to reactance, these inductors and capacitors have power associated with that reactance. It is known as reactive power, and it is mathematically represented with the imaginary number. Okay. Now, the reason this is important is because reactive power is associated with the magnetic field of that inductor. Okay, it's associated with the reactance, meaning it's associated with the magnetic field. It does not do any real work. The real work is done by the real power that is converted to mechanical energy. Okay, the electrical energy is converted to mechanical energy. That is the one that is actually doing the real work, that is spinning those machines. The reactive power does not do any real work. Yet, again, coming back to the same point, it is real. It has a physical basis in real life, meaning when the switch is flipped on and the machine starts churning, when the machine starts swirling, not swirling, getting lost inside my own head. When the machine starts and the motor starts spinning, the reactive power needs to be sent from the utility company all the way to the industrial customer. Switch is flipped on. The coil requires real power as well as reactive power from the utility company. But because it's an inductor, the power is received in one half cycle, and then the negative half cycle, it is sent back out. Back and forth. If it's a small circuit on a lab bench, it is self-contained right there. It does not have to travel a long distance. But when it's hundreds of miles long, that reactive power is traveling back and forth hundreds of miles. And every time it travels, a whole bunch of power is lost as heat. Make sense? So even though that reactive power is not doing any work, it still needs to be sent by the utility company over hundreds of miles, and 60 times a second, it's traveling back and forth. Well, usually it's like 120 hertz transmitting power, I think. And so it requires all of that reactive power to travel back and forth over long distances, with a majority of that power lost as heat. Not majority, sorry. A lot of that power is lost as heat. Okay. And it's lost for nothing. Does that make sense? Any questions?
So
Okay.
reactive power.
Yes, go ahead.
So reactive power is used to create the magnetic field within the inductor?
Yes, it's associated with the magnetic field of that inductor. Yes. So we want to avoid these losses, right? Because the utility company, as well as the industrial customer, would have to set up infrastructure to handle all of that power. Mathematically, we say that this is real power and reactive power. We place a distinction between the two. But in real life, all power is the same. The industrial customer, as well as the utility company, has to count all of that power as the same, right? So you'd have to pay twice as much, depending on how much power you're sending, right? And the associated infrastructure with it, the generators, the safety equipment, the transmission lines, all of that infrastructure has to be able to handle all of that real power as well as the reactive power, which is prohibitively expensive, right? We don't want to do that, obviously. And so we use the capacitor. The capacitor is similar to the inductor, yet it is opposite in many ways, right? It is opposite in many ways. So instead of traveling back and forth, what if we place a capacitor in front of that load? Now, when the power flows out of the inductor, it flows into the capacitor. And when the power flows out of the capacitor, it flows into the inductor. Remember, voltage leads the current for an inductor, whereas in a capacitor, the voltage lags. And so they are 180 degrees out of phase. 180 degrees out of phase. When the energy flows into an inductor in the positive half cycle and flows out in the negative half cycle, it goes into the capacitor. In the capacitor, the positive half cycle, the energy flows out and goes into the inductor. Okay. So instead of traveling back and forth over long distances, if we place a capacitor or a bunch of capacitors right next to the inductive load, the power will flow out of the inductor and travel only a short distance. Does that make sense? Right? When the switch is flipped on, the power will travel from the utility company to the inductive load once. Okay, all of that power will travel over the long distance transmission line only once, after which the power will come from the capacitor itself. So it will just travel a short distance rather than going all the way back and forth. Does that make sense? Let's take a 10-second pause while you think over that and let me know if you have any questions. Does the concept make sense on what a reactive power is and why we use a capacitor in front? The power is bouncing back and forth between the inductor and the local capacitors. It does not have to come from the utility company after that first initial half cycle. The process of calculating and applying a capacitor in front of that inductive load is known as power factor correction. Okay, is known as power factor correction. The required power is noted by power factor, the term power factor. We'll look at the mathematical representation in a couple of slides. The process of calculating and placing a capacitor in front is known as power factor correction. Okay. If you have a large industrial customer that is setting up a new factory, or perhaps the power goes out, right? Power goes out, and now all of the machines need to come online. Well, the customer has to work with the utility company to turn on a staggered turn ons. Okay. You cannot just flip all of the switches on all at once. The utility company would not supply all of that power. It has to be a staggered turn on. If power for the entire campus goes out, the places on campus that have huge electric machines have to work with the utility company to maintain a staggered turn on for all of those electric machines. Otherwise, the utility company does not have the resources to supply all of that power. So, introduce new terms. Let's look at the notations and the units. We'll start with first Q. We are all familiar with P. Power is noted by the letter P, and all of these are uppercase letters, okay? That is the real or the average power is still given by watts. The reactive power is noted by the letter Q, and it has the units volt, ampere, reactive. Okay, volt, ampere, reactive. And because we are placing a distinction between reactive power and real power and representing it mathematically using the imaginary number, when you add up the real and the reactive power, you get a complex quantity noted by the letter S, and that complex quantity is the total complex power. Okay, it's the total complex power where you add up the real power as well as the reactive power, noted by the equation S equals P plus JQ, and the units are simply volt ampere. Volt ampere. Okay. Mathematical representation of total complex power is S equals P plus JQ. And from those three quantities, we can draw a triangle to describe the vectors. Okay. Real power P is on the x-axis, right? Positive real axis. Imaginary power Q, sorry, not imaginary power. Reactive power Q is on the imaginary axis. And here's the beauty of the capacitor and the inductor. For an inductor, impedance angle is positive. The reactance is noted as positive. Hence, QL is positive. Reactive power for an inductor is always, always, always positive. It's the mathematical representation. Again, power in real life is never positive or negative. It's for us as humans to be able to balance out our equations and for our theoretical analysis that we place a plus and a minus sign. Okay. So QL is positive, whereas QC, reactive power for a capacitor, is negative. Actually, QL, QC. This comes from the fact that the voltage for an inductor leads by 90 degrees and the voltage for a capacitor lags by 90 degrees. So plus 90 minus of minus 90 gives you 180. If they share the same current, then the voltages for a capacitor and the inductor are 180 degrees out of phase. The reactances are in opposite directions. Reactance and impedance for a inductor is positive. Reactance and impedance for capacitor is negative. And so is the reactive power. Okay. Just as a final note, in a graphical representation, the amount of reactive power required by an inductive load is given by the phase angle theta. right? The point is we want to reduce that theta as much as possible. So if QC was not there, your total required power would be equal to QL. But now, because you put a capacitor in there, your total power is now reduced. Make sense? These are vectors, so we have to take phase angles into account. QL points straight up, QC points straight down. So we can try and get it as close to 0 as possible. All right, we'll end class here today. We just have one more slide of equations remaining, and then we'll do 2 examples on Wednesday. All right, and that would be it. So I'm around if you have any questions. Otherwise, I will see you all on Wednesday.